So we are now in the sixth lecture for Math 140 Business on September 16th. And last time, to recap, we introduced the idea of a distribution and in particular, the normal distribution. And we then talked about some of the properties of said normal distribution. And today I want to go a little bit more in depth with the normal distribution and actually start solving some problems. So the last thing we did, I believe, was the z-scores. And there are essentially three conceptually different things that play a role when you're dealing with normal distributions. You have your raw data. The raw data are your actual values. You have your z-scores. And you have your probabilities. These are the three things that we care about when talking about normal distributions. And it used to be, back before calculators and computers were so prevalent, but it used to be that the only way to get to a probability from your z-scores, the only way to get to a probability from the raw scores is to pass through your z-scores. You go from the raw data, and then you compute your z-scores, and then from the z-scores, you can compute your probabilities. But now we have methods to go directly from raw data to your probabilities. In particular, your calculator or your computer can do that. But it used to be that the only way to calculate probabilities from raw data is to first compute your z-scores via the formula that we did last time, z equals x minus mu over sigma. And then to go from z-scores to probabilities, you would have to look up a z-table. Z-tables aren't as commonplace as they once were because you have calculators and computers, but nevertheless, I think it's very important to at least see how they work. And we're going to be solving some problems today that work with all of this. So let's start with the following example. You have a situation, it doesn't really matter what the details are in terms of the math, but it is essentially saying that this particular student or this particular group of students needs to score a minimum of an 820 on some score. So a minimum score of 820 is required. Where the scores, and I'm going to introduce a notation here, where the scores, and we do a little wiggle like that, it's called a tilde, capital N, 1010, comma, 214. And that's a shorthand notation. And the question is, what exactly does that shorthand notation mean? There's this thing right here. I want to know what that symbol means, and what that symbol means, and what this number means, and what this number means. All four of those mean something. So, anyone help me out here? What do you think those symbols all stand for? Give me any one of them. Not everyone at once. It's hard for me to hear everyone, talking over each other.
Are the 2 points the x and y or no?
No, so that is not a point.
Would it be max and min scores?
Not max and min. Let's start with the capital N. What do you think the capital N stands for? I'll give you a hint. It's essentially the title of the chapter.
Normal distribution.
Normal distribution. So the capital N is telling us that we're dealing with a normal distribution. Now, knowing that we're dealing with a normal distribution and knowing, or hopefully remembering what I spoke about last time, what do you need to know specifically which normal distribution you're dealing with out of all of the infinitely many normal distributions that are out there?
We need mean and standard deviation.
You need a mean
Yes.
and standard deviation. So what do you think those numbers are?
Mean and standard deviation.
Yes, the mean, and I'm just gonna write mu and sigma. The twiddle in front just tells you that you're dealing with a distribution. So this little twiddle in front, this little thing here, just says that the scores, you know, are represented by a normal distribution whose mean is 1010 and whose standard deviation is 214. And we need a minimum score of 820. The question is, if I pick, let's go back to black. The question is, if I choose at random, what is the probability the person chosen scored over 820? So we're told that we have a normal distribution whose mean is 1010 and whose standard deviation is 214. We're told that an 820 is the minimum score necessary to pass. So if I choose a person at random, what is the probability that a person chosen scored over 820? So while it's not necessary to make a picture, I certainly recommend it, at least when you're starting out, to see what's going on. So I'm going to make a normal distribution curve. My normal curves look like a bell. And where is the mean of this distribution?
In the middle.
In the middle. And what is the value of the mean for this case?
1010.
1010. And we know the standard deviation is 214. So if I move one deviation to the left, physically on the graph, physically on the picture, pointing to the exact spot, where is one deviation to the left of the mean? At least in the limits of our eyesight and my artistic abilities. Where is one deviation to the left of the mean located?
About like where your graph kind of like makes a sharp turn.
So about here?
No. Oh wait,
No?
isn't it? Wait, isn't it on the other side?
Well, it'll be on one side. I can go one deviation to the right and I can go one deviation to the left. 820 is to the left, so that's the side that I care about for this problem. I don't really care what's happening.
Yeah, I think it would be like around there, but maybe a little more to the left.
Okay, so maybe around here or so?
Yeah, probably.
Okay, it's ballpark, certainly in the right ballpark, right? We agree, give or take, hopefully. So what number out of curiosity, what number is that?
796.
796. So where is 820 located?
At the end,
What do you mean at the end?
what, where the loop ends?
Where the loop, you mean over here?
Yes,
You mean all the way to the very far left?
yes. Oh, I'm wrong.
820?
All right, no, I'm sorry.
It'd be
It's
right
a
in
few-
between.
It's a few points to the right of 796.
Okay, so somewhere in the vicinity of, let's say, over there. We agree? Give or take about there?
Yeah.
Yes.
And what we're looking for is the probability of scoring more than 820. I don't care how much more than 820. So what I'm looking for is the area to the right of 820. Do we agree?
Yes.
And that should represent the likelihood of, or the probability of picking someone who scored more than 820. So as a lower bound, right, you could say, oh, it's certainly greater than -2. Well, of course, all probabilities are bigger than -2. So that doesn't really help much. What is a useful lower bound of whatever the actual true answer is? It's guaranteed to be more than this number. What number is a useful lower bound for the area shaded by the yellow? It's certainly more than what? Anyone?
What was your question again?
My question is that we're trying to find the area to the left of the 820, the area shaded by the yellow, right?
Yes.
Give me a lower bound on that. Give me a number for which you're guaranteed to be that the true answer that we're looking for is above it.
That's greater than 1010 right on the other side of the graph.
No, like what percentage of the area is shaded? What we're looking for is the percent of the area that's shaded. So it's got to be something between 0% to 100%.
Oh,
So what I'm looking for is, while I might not be able to know the exact number, I know it's certainly bigger than this.
We know it's certainly bigger than 50%.
We know it's certainly bigger than 50%. Because if I just focus on the left side of the graph, that's already 50%.
It'd be lower than 68%, right?
Not necessarily, because remember, one deviation in both directions gives me 68%.
Oh, okay.
But this stuff here might be more than the stuff that I'm missing.
Oh, okay.
Would it be like a little less than 75%?
Maybe, I don't know. Actually, I do know. It's, I guess an upper bound would be actually, I don't know. I have to think about it. The beautiful thing is I don't need to worry about it because we're going to come up with 3 techniques that are going to give us the exact answer, or at least approximately the exact answer. I just want to make sure that we understand that when we get the answer from our calculator, if we got something like 22.6%, we'd say we did something wrong, and that doesn't make any sense, right? The number should certainly be in the ballpark of 60, 70%, something around there. Does that seem reasonable?
Yes.
Yes, no, makes sense. I mean, let's think about it. This part here, if I go all the way to 796, what percent is that from last time? How much?
68.
That's 68%, right? All of that 68%, which means the outside 2 parts have to total how much?
32.
32, which means this part has to be how much?
32.
15.
Well, no, that's
16.
16%. Because it's 32 together between the left and the right, which means just the right has to be 16. Correct?
Yes.
And 68 and 16 gives us 84. So if I went all the way to 796, that would be 84%. So the best I can say right now is that the answer is whatever it is that I'm looking for is greater than 50%, but it's less than 84%. I can definitively say that. Do we agree?
Yes.
I can definitively say that. So if I got something 70, 75, 80 ballpark, I'd be like, okay, that certainly seems possible. If I got something like 30, 40, 42, even like 51 or 52, I might say that does not seem likely. So the question is, how do we find the area to the left of the curve? And we do it in three ways. So number one, the first way is we're going to compute the z-score. What z-score corresponds to 820? Do you recall the z-score formula?
Yeah, you said it was z equals x minus mu divided by the standard deviation.
Okay, what is my x?
820.
820. What is my mu?
10,
So
1010,
1010. What is my sigma?
214.
Okay, 214. So I take out my calculator now. 820 minus 1010. Get that answer divided by 214. What do I get?
negative 0.8878.
So I'm going to write that approximately negative 0.888. Okay, do we agree with that?
Yes.
Okay. Now, first, even though we don't need to know what a z-score is in order to do the next step, we should understand what a z-score is. The z-score tells you how far you are from the mean in terms of standard deviations. To say my z-score is negative 0.888, or at least approximately so, means that my raw data is approximately 0.888 standard deviations below the mean. If it was one deviation below the mean, I'd be at 796. Negative 0.888 means I'm not quite one full deviation below the mean. I'm less than that, it's about 90% of the way, which is certainly the ballpark of 820. Do we agree? Does that make sense?
Yes.
Okay, so now the question is, how exactly am I going to find that point? And to do that, I'm going to stop sharing my screen here. And I'm going to share my screen on my computer. Am I still sharing? Am I still sharing? Am I? No. Okay. So, okay, here we go. And let's enter the course. Enter the course ebook. And there we go, all the way to the end of the ebook. Uh-oh. Are there no tables here? Where are the tables? All right, well, you know what? I can use the tables from my other course because I know it's there. Okay. All right, so what we have here is a bell curve, a normal distribution. And as you can see in the picture, whatever values we get from this table of numbers, which we'll have to learn how to interpret, it's going to give us the area to the left of the point in question. But in our example, we want the area to the right of the point in question. So whenever I calculate, whenever the table gives me, how do I take this number and get this number out of it.
Do the whole thing like 100% minus that table entry,
Exactly. That's exactly it. So you do 100% minus this percent, it will give us this percent. So when it's asking for to the right, then you do 1 for 100% or 1 if you're in decimal form minus whatever you get on the left. The question is, how do I calculate from this table what I get on the left? Just like, seems like a lot of numbers, a lot of gibberish. So the answer is you go directly to your z-scores. Now your z-scores will be determined from the row heading and also from the column heading. So our z-score was what? I forgot. What was our z-score?
Negative 0.888.
Okay, so this table doesn't go to 3 decimals. This table goes to 2 decimals. It has the first decimal in the row, and then the second decimal is then the column. So I want negative 0.89, which is the closest to negative 0.888, right? So having a 9 as my second decimal will be the last column. And then I'm going to go down to which row? Which row is the right one?
0.
0.
Negative 0.8.
Negative 0.8. So negative 0.8. And then the column is the last one, 9. So this tells me that the probability of being to the left of my z-score, to be the left of negative 0.89, is 0.1867. And therefore, what is the probability of being to the right of my z-score? Anyone? If being to the left is 0.1867, what is the probability of being to the right?
81.33.
0.8133, which is 81.33%. Does that make sense? Anyone? Does that make sense?
Yes.
Are there any questions on how to use the table to find probabilities?
Where would we find the table? Do we just look it up? Or?
Well, your book has one. I have the book right here, and it's actually on the back cover. If you don't have the book, you can just do a Google search for a Z table, and it will most likely be the right one. Whatever link you pick. Different links do it different ways. Some tables, you have to look at the shading. Some of the tables give to the right, ours gives to the left. You could also just do a Google search for a Z calculator, and you don't even need a table. You put in your Z score and it will tell you the answer, which is what, by the way, what we're gonna do in a second. So don't do that now. But if you end up with a table somehow or other, and this is how you use it. Does that make sense for our first method?
Yes.
Okay.
where did you get that 1 minus from?
Well, the book gives us 0.1867. But what the book gives us is to the left.
I see.
don't want-
Oh,
I
so
don't
you're
want to the
doing,
left.
oh, okay.
I don't
Okay,
want to the left. I want to the right.
So you do the 1, which is all the way to the right, minus that small part to get the
Essentially,
percentage.
because 1 is 100%. 1 is the whole thing. You take away that, you're left with this.
Got you. Thank you.
Make sense?
Yes, totally.
Okay.
Thank you.
That only get the right side too then? You said, so there's the left.
Well, the table gives to the left and 1 minus the table gives to the right.
Oh, okay.
Right? Is that your question?
Yeah.
Other tables might give to the right. And if you want to the left, you got to do 1 minus that. It depends on the table that you're looking at.
Okay.
Okay. The second approach is even easier. And to do that, I'm going to demonstrate on the TI-84 plus CE calculator. What I'm going to do is I'm going to hit seconds so I can go into the blue mode, and I'm going to hit DISTR for distributions. And then I get a list of distributions. Which of these distributions, which of these options do you think is the correct one to use? There's only two that might seem reasonable, huh?
Was it the second one?
It's the second one. It's the normal CDF, not the normal PDF. The normal PDF you never want to use. There's no point to use it at this level. So we're going to hit enter for normal CDF, and then we're faced with 5 rows. Lower, upper, mu, sigma. What do you think I want to put in for the lower?
820.
820. What do you think I want to put in for the upper? How high am I going?
1010.
Well, 1010 is not where I'm ending. Right, look at my shaded region.
Could you just put like a big number?
Yes, that's exactly what I do. I just throw in a bunch of 9s. I just hit 9 a bunch of times. I'm going to a really, really big number. So I just hit a bunch of 9s. Now, what do I put in for mu?
1010?
That's the mean, 1010. What do I put in for sigma?
214?
214. Then I tell it to paste it to here, and then I tell it to compute. And what do I get?
The 0.812 or 0.813.
Yeah, 0.813. So compared to my earlier answer, is it approximately the same?
Approximately.
All right, 81.27% is what I get on my calculator. So as you can see, your calculator is close. Which of these two is the better approximation, your calculator or from the table? Which,
Probably
huh?
calculator. probably.
Calculator, because remember what we did? We didn't put in negative 0.888 in the table. What do we put in the table?
We put infinity. Oh, wait for which?
Put 0.89.
We put negative 0.89. We rounded it because our table can only handle 2 decimals. Your calculator doesn't care about that. Your calculator will give whatever you give it, it'll work with. So the calculator is a better approximation. Then, of course, do you really care about 0.06%? Maybe, maybe not, but the calculator is better. The third option is a online program, and there's many of them. I'm going to demonstrate it on Crunchit, which, by the way, is free, and it's a wonderful program. So let me share my screen here. And I'm going to get to Crunchit. I got to go through the homeworks, pick a random question. And so you have this thing called Crunchit. So I'm going to hit Crunchit. That takes me to here. So first, this came from that question that I picked. So I'm just going to delete them because I don't need them for this problem. Okay. Delete column, delete column. Okay. So I want to use my calculator to compute this probability. So without actually telling you which of these buttons to go to, if you had to guess, an educated guess, which of these tabs do you think we want to start with?
That says distribution calculator.
Okay, and in the distribution calculator, which of these subcategories do you think is the correct one?
Normal.
Normal. And for mean, what do you think we want to put in?
1010.
1010. And for sigma, what do you think we want to put in?
2014.
Not 2014. I think it was just 214. right? Just 214, correct? Yes, anyone?
Yeah,
Okay. And for probability, which X value do we want it to compute the probability for?
Eight 20,
820. And do we want to be less than that or greater than that?
greater than that.
And then we calculate. And not only does it give us the value that we got from the calculator to a lot more decimals, but it also gives us a nice little picture to make sure that we're looking at the right thing. Does that make sense?
Yes.
Anyone have a question on using either the table or the a calculator or some kind of online program? Of course, they're all different. They require different inputs and whatnot. But Crunch It is a free one. So
Professor?
Yeah.
So the 81% is from the 820 all the way to the right?
that's correct.
Got it. Thank you.
That's correct. Okay. Let's do another one. A little more challenging. Example. Let's switch to green. I haven't done green in a while. Example. Okay. We have this, it looks like it is the same. Yeah, so we still have the same distribution, 1000 and 1010, 214. Okay, we have the same distribution. And the question is, what proportion of students or people, whatever, score between 720 and 820? What proportion score between 720 and 820? And I'd like to do this using the table, and I like to do it using the calculator. I don't need to do Crunch It because Crunch It and the calculator are really the same. If you can do one, you can do the other. So let's do the table first. How would I use the table? First, strategically, before we actually get into the actual math. How would I use the table to determine the probability of being between 720 and 820? Because remember, the only thing the calculator can give you is to the left of a number. Of course, you can do 1 minus that to get to the right of the number. So
You
left
could-
or right, huh?
You get the C score for both of them, and then you would subtract the first C score to the second one.
So you want to subtract their Z scores. Is that what you're saying?
Well, the percentages.
Okay, that's what I'm talking about. So let's just do a picture to see what's going on here. So here is my normal. What's the center?
10-10.
1010. We know that 820 is somewhere around here. And we know 720 is, somewhere around here. And what we're looking for is the area between them. So what I'm going to do is I'm going to calculate each Z score. Now, of course, I should already know the Z score for the 820. What's the Z score for 820? To 2 decimals?
The 0.888.
The negative 0.888 or approximately negative 0.89. And what is the Z score for 720?
Negative 1.355.
So to 2 decimals, negative 1.36. And again, it's an approximate. Right? So what we're going to do is we're going to calculate the percentage that comes from the 820, which remember is everything to the left of 820. We're going to calculate the percentage that comes from the 720, everything to the left of 720. And then what will we do with those two numbers?
We'd subtract.
We'd subtract them. So let's go ahead and load up that table, which I hope is still here somewhere. And I hope I didn't lose it. I think I have to load it up again. So okay, so we already know the negative 0.89, but let's just write it up again. What is the percentage that comes from negative 0.89?
.1867.
0.1867. We had that before. Remember, we went to the left here, so it's not 1 minus because the left is the correct side. And what is the percentage that comes from the negative 1.36? Anyone there?
Would it be 0.0885?
I don't think so.
How does it go by? Is it point? So how do the columns go by again?
Well, the last column is 9.
9. Okay.
So 9876.
Is it 0.0869?
0.0869. Right, starts with 0.00 up to 0.09. So negative 1.36 would be 0.0869. So if I go back to my notes here. I had that 0.1867 is everything to the left of 820. That's 18.67%. And then 0.0869 is everything to the left of 720. And therefore, what percentage are between 720 and 820? According to the table,
0.0998.
so 9.98%. 9.98% will be between 720 and 820. Okay, and now let's use a calculator. Okay. So where do I go?
Second and then district.
Second in the distribution, and then which one do I want to use?
The second one.
The second one, and what do I want to put as my lower?
720.
720, and what do I want to put as my upper?
820.
820, and with what mean?
1010.
What deviation?
And 20. 214.
Enter, put it there, enter, and what do I get?
9.96%.
Which is pretty close to what I had before. Enough so that I don't question it, right?
Yes.
So 9.96%. Again, I'm only off by 0.02%. So it seems fairly accurate. Does that make sense so far?
Yes.
Okay. Now, new question. How high must a person score to land in the top 10%? How high must a person score to land in the top 10%? So how does this type of problem compare to the problems that we've done up until now?
We're given the C score, right, that we want instead of the.
Well, we're
instead-
not actually given the Z-score. We're given the probabilities. We know that it's 10% to the right, 90% to the left. We're not actually given the Z-scores.
Oh, okay.
And we're certainly not given the raw data. In fact, that's the question, right? What data corresponds to that 10% cutoff mark? And if I make a table, and not a table, but if I make a curve with 1010 here in the center, approximately where is the 10% cutoff mark, give or take? Doesn't have to be perfect, but approximately where is the 10% cutoff mark?
Like pretty close to all the way on the right side. Yeah.
All right, maybe something like that.
Yeah.
Okay, so the question is, what is that point? And again, we can do this in two ways. We can do it with the tables, and we can do it with the calculator. And we're going to do it in actually three ways. I'm going to use Crunch It for this one. Crunch It, for whatever reason, there's no program built into Crunch It that will compute between 2 points. It seems like with everything else Crunch It can do, I'm a little surprised that they don't have that. Crunch It has to the left of a number and to the right of a number. Crunch It doesn't have in between. My calculator does, but Crunch It does not. It's very weird. But in this case, we'll do it in all three ways. So first, let's use the table. But there's one problem already with the table. How do I start with the table? I look at the Z-scores and I compute the probability. I don't have the Z-scores here. So how am I going to use the table?
You're gonna look for the one that has the probability you want.
Exactly. I'm going to look inside the table and identify the one that has the probability that I want and work backwards. Now, is it going to come in this pages table or is it going to come in the second pages table?
The second pages table.
Second page, because remember, I'm looking for the cutoff, which is on the far right. It might be shading to the left, but the Z-score is still on the right. Here, Z-scores are on the left. Here, Z-scores are on the right. So it's certainly the second. And even if I didn't see that, you look for the number that you're looking for, which by the way is not 10%. What am I looking for in this table?
Be 0.1.
No, I'm not looking for 0.1.
0.9.
0.9, because remember the table gives to the left. I want 0.1 to the right of some point, which is 0.9 to the left of that point. You agree?
Yeah.
So I'm looking for 0.9. So I'm looking here and these numbers are getting bigger. They're getting bigger, they're getting bigger, they're getting bigger, but I don't see no 0.9. So let's move to the next page. Do you see any 0.9 anywhere? So where's 0.9?
Like,
1.2 and then
yeah, 1.2 and 0.09.
Would it be 1.29?
Well, so that's the question. Look at 1.29. That will give me a Z-score of 0.9, a probability of 0.9015, right?
Yeah.
And if I go one before that to 1.28, that will give me 0.8997.
That's closer, right?
That's closer, right? It's not all the way, it's not perfect, but it's closer. So if I had to pick, I would guess about 1.28, and then what decimal would kind of be reasonable for something that's 0.0003 from this one, but 0.0015 from this one. What decimal would you pick for the next dot? Next decimal place, 1.28, and then what would you put next?
2.
Okay, that's what I would pick. In fact, that's what I did pick, 1.282. So with that knowledge of a z-score of 1.282,
We can't,
huh?
I was gonna say we couldn't see it, but you fixed it.
Yeah, I was loading it. 1.282. The question is, what raw data corresponds to a z-score of 1.282? The table got me from probabilities to z-scores. How do I get from z-scores to raw data?
That's when you would plug it into the equation.
What equation?
The one to calculate the z-score, so z equals, is it x minus mu divided by the standard deviation?
Okay, so if I want to rearrange this to solve for x, what would it be?
Z times the standard deviation,
Yeah,
Plus mu.
plus mu, yeah.
okay, I'm just going to write it a little differently, but yes. The standard deviation times z plus mu. So let's go ahead and compute it with our numbers. What do I get?
We're not using the same values from before, or we
Yeah,
are?
yeah, because it's 1010, right? So it is the same problem. It's a continuation of that problem.
Would it be 1,284.348?
Yeah, so about 1284. In fact, I think SAT scores are only every 10, so technically it should be 1290. Because 1280 is not high enough and 1290 is high enough, so we pick 1290. Does that make sense?
Yeah.
All right, next. Calculator.
So why did we choose the 1.2 on the table?
1.2 on the table? You mean 1.282 on the table?
Yeah, like why did we go on the 1.2 row?
Well, we're looking for 90%, which is between these two numbers here. Right, somewhere between this number and this number, I hit 90%, right?
Yeah,
That's
I see. So it hits the 1.2. Okay, I got it. I got it.
1.2 and then somewhere between 8 and 9. So I approximated, I did 1.282.
Got it. Thank you.
All right, no problem. So now let's use our calculator. What do you think I'm going to go to on my calculator?
Second distribution,
Okay, good start. Second distribution. Where now?
and then the second one.
Well, the second one requires knowing lower, upper, mean, and sigma.
Oh, okay.
And we don't have a low, I mean, we have an upper, but we don't have a lower.
Inverse norm.
Inverse norm. Excellent. We're going backwards here. The inverse norm. And on my calculator, I got a lot of options here. Not only do I have mean and sigma, of course, but I have the area and whether I want that area on the left, in the middle, or on the right, which the TI-83 does not have. And I don't even think some of the other 84 versions have it. So in our case, what area do I want?
The right side.
Okay, and what area do I want for that right side? How much area?
Percent.
0.1 with what mean?
1010
And with what sigma?
to 14.
214. So I would put in this. Now, if you don't have a calculator that gives you these options, it probably only allows you to the left. Which means what area would you want to put in if you can only do to the left?
0.9.
0.9, but I can do it to the right. So when I do it, I get this, and then I hit the enter, and what do I get?
Pretty much the same answer.
Pretty much the same answer. Which is really reassuring. So this is from tables. And then we have calculator, which gives us, again, 1290. And then we're going to go to crunch it for the third and final way of doing it. Crunch it. So when I go to crunch it, I'm going to share my screen here again. And here's crunch it. Okay. So I'm going to get rid of this. Okay. So we're on crunch it. So where do you think I go to amongst these headings for this particular calculation?
Distribution calculator.
Okay. And which one do I want to go to?
Normal.
Oh, wait.
Good guess. We're still dealing with a normal curve, right? What mean do we have?
Same.
Same.
Same, standard deviation?
The same.
Same, but here's the problem. It's asking us to put in the likelihood, the probability of being greater than some number or maybe less than some number, but we don't know this number. In fact, that's what we're looking for. So what do you think I do? How do I get around this issue?
What's the quantile do?
What does a quantile do? I don't know. What does the quantile do? That's a great question. What do you want to guess we would put in here if the quantile was the correct tab?
Would it be 90% or?
Well, let's take a look. 0.9, let's calculate.
Yeah, that's about the same.
That's pretty much exactly the same with like 8 extra decimals of precision. So that's exactly what quantile does. But quantile is only to the left. Doesn't have the option to the right or center. It's always to the left. So when you hit the quantile tab, you're computing the likelihood of being less than some number is that quantile. In this case, 90%, 0.9. You solve, you get the answer. So crunch it gives the same thing as the calculator and the table in this case, at least, to the necessary precision. Does that make sense?
Yes.
So are there any questions on chapter 3? Because that's pretty much it. I want to do one more example, but this is essentially it. It's all about the normal distribution and converting from raw scores to z-scores, or raw data to z-scores to probabilities. And if you can understand how to use your calculator or an online program like Crunchit, or you can do it like from the tables, then there is no question in chapter 3 that you should not be able to answer. Right? So are there any questions on what we've done so far today?
Can you show how to do it on the calculator again? I'm doing it on my calculator and it says I have an error.
So do me a favor, if you don't mind. I'm gonna unshare here or stop sharing. Can you share your screen so that I can see? You're not talking anymore, but hold it up.
I was doing this one. I'm on the calculator and it says that I have an error. So I was gonna ask, can you show them how to do it on your computer, on your
Can you
calculator?
but bring it closer because I can't see it. Okay, hold on. So it's not 1, it's 0.1.
Oh, it's 0.1? Okay.
Yeah, because it's 10%, not
Oh,
not
okay,
100.
that's
1 is 100%.
Oh, okay. Thank you.
All right, so that doesn't make any sense. That would, be infinity essentially. Okay. So I'm going to share again. One last question here.
Thank you.
No problem. So here's one last example. So we have a situation that's normal with the mean of 170 and a standard deviation of 30. Again, the context is irrelevant when it comes to the math. But of course, if you're actually solving a problem and the answer is 26 miles or 82 kilograms or 34 seconds or whatever the case may be, obviously the context and the units matter for the, for the overall problem, but they don't matter for the math. So the question is, what is the first quartile, which we know as Q1. What is the first quartile? Now, your first instinct might be, wait a second, quartiles. But that has to do with the median and box plots and not normal distributions, right? The first quartile, if you recall, was, you first find the median and then you look to the left of the median. So you find the median to the left and hey, that's the first quartile. That's nothing to do with what we're doing now, right? But you'd be wrong. Because the first quartile just means, what is the point that cuts, well, actually, before I say the answer, let's remind ourselves, if I have a box plot, each of the 4 sections is what percent of my data, approximately?
5%.
25?
25%. Which means the first quartile is just the points at which 25% is to the left. So I don't need a box plot to have that concept. I can just say it's about here somewhere, and that's cutting off about 25%. Actually, probably it's a little further. I'm not the greatest at drawing, but let's say something like this. So how do I find the point at which 25% of the data is to the left?
We do the inverse norm like we did last.
Why not? Let's do the inverse norm. So second distribution, inverse norm, area is how much?
25%.
25%. Mean is what?
170.
Sigma is what?
30.
Left, center, or right?
Left.
Left. So I have this 25% area, mean sigma left, and oops, go down one. Enter, enter, and I have that the first quartile is about, what is that, 149.7? 149.8. First quartile. Does that make sense?
Yes.
So using a calculator, 149.8. What's the z-score? What's my z-score? It's not in your head. You gotta do some math here. Compute the z-score.
Would it be negative 0.67?
Yeah, approximately negative 0.67. So that means roughly 2/3 of a deviation below the mean is the 25% cutoff, is the first quartile cutoff. This is universal. This is true for every normal. The first quartile will always be 2/3 of a deviation below the mean. This, of course, is only true here because this is raw data and that depends on this mean and this deviation. But the z-score is universal. By the way, where's the second quartile?
50%.
Well, in the middle. All right, the second quartile would be 170. Right? It cuts off 50%, but the quartile itself would be 170. Does that make sense?
Yes.
Any questions on what we did today?
No.
I was gonna ask about, like if on the test, if it was to the, like if the graph showed something to the right for our calculator, we would have to do a percentage for the left on, if we don't have the.
Yes.
Okay.
If you don't have in your calculator the ability to choose left, right, or center, then your calculator, I believe, you might want to check on this before the test, but I'm pretty sure your calculator inherently does left.
Yeah, because I think when I put 0.90, when you said to put 0.9 instead of the 0.1, it did do the correct answer.
Yeah, I'm almost certain. I'd be willing to bet your life on it. So not mine, of course, but yours. That it's to the left.
Okay, thank you.
Right? Any other questions? Going once. Twice. 3 times. All right. Well, in that case, I'm ready to call it a day if you guys are. Anyone complain about ending a few minutes early?
Nope.
You sure? I mean, you're paying for an education. I don't want to shortchange anyone. You know, you might say, hey, no, I'm paying for this, but no one seems to care. Okay, so be it.